try to make up something, okay, before in such a short time. But on the other hand, that also means that the shape it is presented to the audience that's usually not satisfactory. Okay, so this is what I just would like to talk about something about the homework stuff. Yeah, just as a recap, let's get started for our 6.1. So my goal is to finish 6.1, the Laplace equation, and also, of course, that also include the Poisson's equation. And let's see how much that we can do for 6.2. Okay? So again, Laplace at the beginning of the chapter 6, I asked you folks to try to put everything about the Fourier transform stuff aside for a while, okay? But don't put that bar too far away, because it's going to the materials of Fourier transform, the Fourier series are going to join us again, okay? Soon after we get into system. Okay. So again, Laplace equation. Laplace equation, which is that again coming. This is just simply trying to reformulate what I've said in the last time, in the last part of the last lecture, which is that for let's say for okay, so first of all, we're talking about 6.1 Laplace equation, okay, Laplace equation, and or Poisson's equation. Laplace equation. The reason we say that's a Laplace equation is simply because we're having Laplace, okay, Laplacian. So Laplace of a function is 0. Okay, this is the so-called Laplace equation. This is probably one of the PDE that we are touching with the simplest, okay, formulation. And in 1D, okay, in 1D that simply means 1D space. That simply means uxx equals to 0. Okay, this is in 1D. Okay, and that also means that uxx plus uyy equals to 0, or uxx plus uyy plus uzz equals to 0 in 2D and 3D. Okay, and in 1D the solution is actually going to be very straightforward. The only possible solution is going to be something like ux equals to ax plus b. There's nothing else. This is the everything that it could ever include. However, when you see that the possible class of solutions, okay, in 2D and 3D, actually, the possibility becomes much, much richer. And in this case, we'll be calling our u to be harmonic, okay, harmonic functions. The reason that the harmonic functions are so important, such that we want to use such a significant name, okay, to describe it. Okay, the reason is that okay, the harmonic functions or the solutions to the Laplace equation, they are usually stands for the steady state. They usually stands for again Laplace u equals to 0. This stands for steady state. Okay, steady states of wave equation, and heat equation. Okay, because the wave equation, heat equation, what is that? That's simply utt equals to c squared uxx. Well, okay. Let's say in the 2D or 3D case, c squared Laplace u and ut equals to d Laplace u, right? Okay. So again, when u is not changing on time, that means that ut is 0 and utt is also 0. That also means that our Laplace u is 0, which will lead to the solution to the Laplace equation. Similarly, if we are having, so this is for the case of homogeneous. Okay, this is for the homogeneous scenario. Okay, if we're talking about inhomogeneous, when we're talking about inhomogeneous equations, for example, let's say utt equals to c squared plus u and then plus f. Okay, then let's say fx, and then ut equals to d Laplace u, and then plus fx. Okay. Of course, the x over here, it's not a single variable. Well, okay, so it's not one dimension anymore. The x over here should be regarded as a vector. Okay. So this is the case for inhomogeneous equation. Okay. This is the case for the inhomogeneous equation, and correspondingly, their steady states could be described as something like, okay, Laplace u equals to something like, let's say fx. Well, probably you don't want to use f because I have already used x. So what about for consistency of the notation? What about I change things over here from f to g? This is probably better, right? Okay, so let's say gx, and here the fx is just simply a linear, a linear reformulation of the g over here. Okay, just negative g divided by c squared or negative g divided by d. Okay, so this is the so-called Poisson equation. Okay, this is the so-called Poisson equation. Okay, well now before we move, so first of all we have really illustrated the importance and our motivation to study the Laplace equation. But let's still try to use several examples, okay, to see that why the Laplace equation is so important and how to obtain some examples, okay, some very easy to memorize examples for that. Okay, so let's say examples for Laplace equation. Okay, examples for Laplace equation. Well, so let's say the first equation. Well, it's actually the example. So I'm actually simply going to illustrate the examples, actually 1 to 4, on page 100 and 153. So the first one is comes from the electrostatics. Okay. So this example will make perfect sense to you if you have the background of some electrostatic physics, but it doesn't make sense to you at all if you don't have that kind of background. But what I'm going to do is that I'm just simply write down that, let's say, I'm going to use E, okay, E, this is a function of x, this is a function of x. E stands for the electricity field, okay? The E stands for the electricity fields. And from the Maxwell's equation, right? From the Maxwell's equation, we had that the curl of E equals to 0, and the divergence of E equals to 4 pi rho, where rho is the charge density. Okay. So the first equation. Well, I understand that you may have already forgot what does it mean by the curl, okay, of a field, but it doesn't matter. So let's say this curl. Okay. So let's say equals to 0. That actually implies that my E can be written as a negative gradient of a function phi. Okay, now and my phi is a scalar function. Phi is a scalar function. Okay, phi is a scalar function. Therefore, again, gradient of phi means, so this actually means negative, okay, number phi. Okay, so that means that, the Laplace of my phi, the Laplace of my phi can be written as, first of all, the divergence of gradient of phi This is how Laplace is defined, right? This is how Laplace is defined. The gradient, that's the divergence of the gradient phi, okay, which equals to the actually negative divergence of the electricity field, which is exactly negative 4 pi rho. Okay, so this is exactly the Poisson's equation. This is exactly the Poisson's equation. Okay, satisfying that the right hand side, our f, okay, our f over here is a constant, negative 4 pi. Okay. Rho, sorry?
Professor, is rho a constant or is it a function?
Rho is a constant. Yeah, rho is a constant. Rho is the charge density. Rho is a charge density. Okay. Rho is the charge density. Okay, so this is the first example. The second example, okay, the steady fluid flow. Okay, steady heat flow. Let's say steady heat flow, steady fluid flow, and steady strain. Okay, and all of these will finally come to that. Okay, all of these things will come to that. Okay, so the Laplace of u. Okay, that equals to 0. Okay, this is the second example. The third example is actually a little bit more interesting in the mathematical fashion, which is about the analytical complex functions. Okay, analytical complex functions. Well, talking about analytical complex functions, we need to first define what is meant by a complex function, right? So a complex function means that, so I'm having my f, okay, I'm having my f, and this function is taking, okay, this is the input to this function is a complex variable z, okay, and the output of this function, f, is also a complex variable. Okay, z is a complex number. Z is a complex number, and my fz is also a complex number. Okay, so that means that my z, of course, that equals to x plus iy. Right? My z is actually x plus iy. And there are, of course, many different ways for me to obtain such a to define such a variable. Such as, for example, okay, so that's such as, let's say f1z equals to z squared. Okay, f1z equals to z squared, which means that whatever z, which equals to x plus iy, I obtain over here. Okay, I just simply square it and then obtain what is the output. Okay, for the what is the output for the complex value. The second function that I define, let's say, equals to z bar, which is the conjugate, the complex conjugate of z. So in this case, my f2x equals to x minus iy. Okay, x minus iy. So what I would like to stress is that in the complex variable theories, there is a fundamental difference between the f1 and f2, which is that my f1 is an analytical complex function. Okay, my f1 is analytical. Okay, and my f2 is not analytical. Why do I say that? Okay, so there is actually, the precise definition of an analytical function, analytical complex function, actually, it requires some time to elaborate. However, a very intuitive understanding of this is that whether a complex function is analytical, it depends on when my z enters this function. Okay, should I tear it apart into x plus iy to perform my computation or not? If I need to deal with the x and y, okay, which means the real part and the imaginary part, separately, like the complex conjugate over here, then it's not analytical. If my z can be treated as a whole thing, then it's usually analytical. Is that okay? Is that part okay to smooth to understand? You see, what do I do with the complex conjugate? Actually, I cannot obtain exactly what is z bar unless I break my z into x plus iy, and then I keep my x is the same, and then I turn the iy to negative iy. Right, so that's the so-called, I'm tearing the complex variable into two parts. But when I'm doing a square, okay, I'm not involved in that such kind of process at all. So is it good? Okay, I'm not involved in such kind of process at all. So more, so let's say a more formal definition, okay, of complex function, which is that it depends on if my fz, okay, can be always written into a Taylor expansion, okay, if my fz can always be written into a Taylor expansion of z. Sums from n, starting from 0 to infinity, a n z n times. Okay? If my fz can always be written into a Taylor expansion of z, then my fz is analytical. Actually, you can see that actually this is the same definition for a real function, for a real variable function. Okay, is analytical. Okay, when I'm saying that a real function is analytical, that also means that my fx, okay, can be always written into a Taylor expansion, okay, of x, and that Taylor series is convergent, no matter what x that I choose. Okay, and this is the same formulation. Okay, when I'm saying that a complex function is analytical, if I can always take my fz into a Taylor expansion, okay, as this. Then the theorem, there's a theorem, okay, which I do not intend to prove, which actually it doesn't take you a lot of time, but I just simply don't want to get into here because this again this will blur our main point over here. Okay, so again, the theorem is the so-called Cauchy-Riemann equation. Okay, Cauchy-Riemann equation. Let's say for any, okay, so for any fz that's analytical, okay, for any fz that's analytical, of course, since this is a complex variable function, and the outcome is also complex, right? So my fz also has a real part and an imaginary part. So my fz, of course, it can, it doesn't have to be analytical. Any complex function fz, okay, can be written into, let's say, uz and then plus ibz. Okay, uz plus ibz. So what's good? And of course, because this, and don't forget that because my z, okay, my z equals to x plus iy, so this also equals to u, okay, x plus iy, and plus iv x plus iy. So that means that my u and v, they're actually both functions, 2D functions for x and y, right? So the Cauchy-Riemann equation asserts that, okay, we always have partial u, partial x equals to partial v, partial y, and partial u, partial y equals to negative partial v, partial x. Okay, these two things has to be true at the same time. It's actually not so hard to prove it. Okay, this is actually one of the exercises. This is actually one of the exercises. Okay, so which means that. And so first of all, an analytical function of z, okay, it has a real part, it's an imaginary part. The real part is u, and the imaginary part is v. And the real part and the imaginary part of an analytical function are actually, there is actually a very strong, there's a strong link between them through the first order derivatives. Okay, through the first order derivatives. Again, without these two requirements, my fz is not analytical. Actually, the Cauchy-Riemann equation is both sufficient and necessary. Okay, which means that if I'm having an analytical function, then I have to have, then the Cauchy-Riemann equation has to be satisfied. And for any complex function satisfying these two equations, then we can prove that it's automatically an analytical function. Okay? But my point is that, you see, here I'm having, this is again partial differential equations, right? This is again partial differential equations. So let's see what would happen to uxx. What would happen to uxx? Well, you see, uxx is what? Uxx is actually ux taking x derivative, right? But according to the Cauchy-Riemann equation, what do we know about ux? What do we know about ux? It's actually vy, right? It's actually vy. So that's good. Which is my vyx. But again, I am allowed to switch the order of differentiation as much as we could. So this is again v. Okay, this is this now becomes vx. Okay, y. Again, what do we know about vx? What do we know about vx? It's negative uy, right? Which is negative uy. Y. So again, negative uyy. See? So if I put the uyy back from the right side, I obtain uxx plus uyy equals to 0. This is exactly a Laplace equation, the solution of the Laplace equation. And similarly, we will be able to derive that vxx plus vyy has to be 0 as well. Okay, so this is again deriving. Okay, this is again deriving a very important, relation between the partial differential equation and the complex variables, which is that, the real part, the real and imaginary part of an analytical function, okay, are both harmonic functions. Or, in other words, they should be the solution to the Laplace equation. Okay, they should be the solution to the Laplace equation. Okay, so so this is it. And okay, one more example. Okay, one more example. So, example number 4, which is the Brownian motion. So in the previous lectures, we have established that that we can describe the Brownian motions, which is that a point, okay, is moving completely randomly in the space. Okay, then we can derive the evolution of the probability density distribution, okay, of such a point by the diffusion equation, right? Which is that ut equals to d Laplace u, okay? Laplace. We have this, okay? Well, if I am having, let's say I'm having the Brownian motion. We're talking about the Brownian motion in certain domain D. Well, okay, I have already used my D. So let me call this guy to be. Let's just say we don't have it. We're not having a speed. Let's say the speed is 1. Diffusion speed is 1, and that doesn't really matter. So let's say this is my domain D. Okay, this is my domain D. Now this is the rule. Okay, now this is the rule of the Brownian motion. So first of all, the starting point can be anything. Okay, the starting point can be anything within this domain. And this point, if I'm starting from here, I'm just going to be going completely randomly. Okay, going completely randomly. And now let me split. Let me split. Okay, the boundary into 2 parts. So this is my part 1. Okay, the red part is my part 1, and my black part is part 2. Okay, so this is the rule of the Brownian motion. This is the rule of the Brownian motion. So whenever the point hits the boundary, then it stops. okay, whenever the point hits the boundary, then it stops. That means that, okay, so a point, let's say a point, it may start over here and then go completely randomly, let's say hit this place, right? Okay, then it stops. Then it stops. It is absorbed on the boundary. Or a point can start over here and then going here, and finally hits here. Okay, and now it stops. So is it good? Okay, now it stops. So you see, the ending of the story is actually binary, right? It should either hit the red part or hitting the black part. There's no other choices. Okay, there's no other choices. So now, let's say starting from, let me use ux. Okay, let me use ux to describe the possibility. Okay, the ux to describe the possibility of a random walk. Okay, of a random walk, starting from x, okay, and hitting the red part of boundary. Because it's, this actually, as long as not starting from exactly from the boundary, then there will always be two different choices or two different possible outcomes, okay, of the end of the story, right? So because you see, let's say if I'm starting from here, then there's possibility that I goes to this red part, but there's also a possibility that I go to the black part. Okay, it's just that the closer that I am to the red part, okay, then it seems that the more likely for me to end at the red part. So, okay, so now can you please tell me what is the possibility? Okay, what is ux if my x is over here? Let me use the color. Okay, let me use this color. Okay. What is my ux? What is my ux if I am starting from the yellow point? What is ux if I'm starting from the yellow point? 1. Because of what?
It's already.
Because it already starts from the boundary. It cannot go anywhere anymore. Okay, it cannot go anywhere anymore. So my u red point, or my u yellow point is actually 1. What is? Let me use another point. Let's say here. I'm starting from here. What is my u blue point? This is what? What is the function value of u of if I'm starting from here? 0. Why is 0? Again, it starts from the boundary. It cannot go anywhere anymore. So there's no chance that it hits the red part. Okay, so that is 0. So what's it? So that basically says that. If I'm calling the red part of the boundary to be my gamma 1, okay, and the black part of the boundary to be gamma 2, then of course the boundary of the optical mean-t is actually the union, okay, of gamma 1 and gamma 2. Right? And we are having that u, okay, u x equals to 1 if x belongs to gamma 1, and ux belongs to 0 if my x belongs to gamma 2. Right? This is what? This is the boundary condition. Okay, this is the boundary condition. And what partial differential equation does my u satisfy? What is the partial differential equation does my u satisfy? Well, again, this is the steady state of a Brownian motion, right? This is the steady state of a Brownian motion, and so of course my u should satisfy that. My Laplace u, okay, equals to 0. Laplace u equals to 0. So is it good? My Laplace u equals to 0. So this is again. So this is again an example. okay, about the application of the Laplace equation. Okay,
它不是等于
so yes, okay.
UT 完了。
我不太懂。
Okay. So before we okay. So section 6.2 would discuss section 6.2 and section 6.3. We will in the next two sections we will be discussing the specific some the detailed technical issues about how do we solve the Laplace equations or the Poisson's equations when we are looking into specific domains like squares and circles or spheres or cubes or spheres. But now before we are going there, just simply as what we have been doing for the heat equation, we'll be first talking a little bit about the well-posedness, about the well-posedness of Laplace equation and the Poisson's equation as well. The Poisson's equation as well. Again, can anyone remind me what does it mean by the well-posedness of a partial differential equation? Uniqueness and existence, and then
Stability.
stability. What does stability mean? What does stability mean? Well, uniqueness and the existence, they are very, very easy to integrate. Which means that I should have a solution and there's only one solution. That's it. But what does the stability mean?
For a small perturbation of the initial condition, the result shouldn't be like too far.
But is there any initial condition anymore? There's no initial condition, there are boundary conditions. So which means that when I'm perturbing the boundary conditions a little bit, then the solution will only change a little bit. Unless we won't be able to prove that. We won't be able to prove the well-posedness for the Laplace equation. Again, if unless I am willing to use the next one hour to delve into that topic, which I'm not willing to. So what we're going to do is the following. We will be establishing one thing that sounds very familiar to you, which is so-called the maximum principle. We derive maximum principle for what? For the diffusion equation. Now we're going to derive the maximum principle again for the Laplace equation. You are going to see that the flavor of the two maximum principle actually are very alike to each other. And this is exactly because that the Laplace equation is exactly by solving the Laplace equation, we are solving the steady state of the diffusion equation. So we'll be only first talking about the maximum principle. And then we will be using the maximum principle to derive the uniqueness of Laplace and Poisson. The other two things, the stability and the existence of the solution, very unfortunately, they actually depend on the specific choice of the boundary conditions. Although for the most common and regular boundary conditions, we can still prove the existence and the stability of the solution. But very unfortunately, for some very bizarre boundary conditions, there is not necessarily a solution. If there is a solution, it doesn't have to be stable. That's why we choose to first prove the maximum principle, and then we go to the uniqueness, because what you're going to see is that the proof of the uniqueness doesn't rely on the choice of the boundary condition. So one more comments about this is that this is a very funny phenomenon. You are going to see that we can prove the uniqueness of the Laplace equation no matter for what type of boundary conditions, right? That means that for certain boundary conditions, there are literally no solutions at all. But if there exists any solution, there should this is the funny part about it. Okay, so let's first talk about the maximum principle. So what's the maximum principle? What is the maximum principle? That means that, again, okay, let my D be a connected bounded open set. Okay, a connected and bounded open set. Okay, in Rn. My n can be 1, 2, 3, or anything. Okay, in an n-dimensional, in an n-dimensional space. Okay, and again, let my ux, okay, let my ux be a harmonic function. Okay. Let my ux be a harmonic function, which means that my the Laplace of my u, okay, has to be 0. The Laplace of my u has to be 0 for any, okay, for any x, okay, for any x within my D. Okay, and my ux, okay, let's say my D, let's say the closure of D, okay, the closure of D. So again, this means the closure, okay, the closure of D, because we were saying that D is an open set, right? D was an open set. So the closure of D, which is D, okay, D bar, which is the union between D itself and the boundary of D. Okay, the D itself and the boundary of D. So that's called the closure of D. Okay. So of course my U, okay, this function has to be continuous. Okay, this function has to be continuous. It has to be first order differentiable. It has to be second order differentiable. Okay, all over D, the closure of D. Okay, then the maximum, okay, the maximum and minimum of ux is only attained, okay, on boundary, on the boundary, okay, on the boundary, which is the partial heat, okay, and nowhere inside. Nowhere inside, unless, okay, unless my u is a constant. Unless my u is a constant. So, first of all, what does this maximum principle asserts? This maximum principle asserts that, okay, so for any domain, you see, I have no restriction of the domain unless it's a connected domain. Okay, it's a whole thing. It's a connected domain, and it's a bounded open set. Okay, and for any domain and for any harmonic function within this domain, then it's satisfied that the maximum and the minimum, both the maximum and the minimum of the harmonic function can only be chosen. Okay, can only be chosen on the boundary of the domain. Okay, and more strongly, it tells you that the maximum cannot be achieved or cannot be attained inside this domain. If that happens, if there is ever a maximum or minimum attained within, okay, inside, strictly inside the domain D, then this function, this harmonic function, is merely a constant. Of course, constant is always a harmonic function, right? Because any order of derivative of a constant is 0. Okay, so of course I'm having my Laplace u is 0. Okay, so this is actually a very strong. This is actually a very strong argument. This is actually a very strong argument. So how is that proved? Okay, well, let me first tell you a fake proof. Okay, a fake proof. Let me first tell you a fake proof, which is again a very intuitive way to tell yourself that this is true. Okay, but it's just that I mean, it sounds like very good. It sounds like very concise, but it's just that it doesn't work. Okay, but I mean, it's intellectually stimulating. That's why we're still talking about that. The fake proof goes as follows. Okay, let's say if I am having a maximum, let's say if I'm having a maximum taking place inside a domain, what does a maximum satisfy for a continuously differentiable function? For, let's say, for a second order differentiable function, what does a maximum satisfy?
First
Let's
order.
say I'm talking about,
the directional derivatives are also.
okay, what does the maximum satisfy?
It's the directional derivative.
The second order derivative should be what?
Second order, negative.
First of all, this first order derivative should be what?
Zero.
Zero.
Its second order derivative.
Negative.
Is that true that the second order derivative is strictly negative? Is that true? Okay.
Yeah.
Can I have something like this? Okay. Then the maximum. Okay. Assuming that this is a straight line. Okay. Then the maximum is all over here, and the second order derivative is zero. It's not strictly negative. But okay. But if I can say, again, this is not true. Okay. But if I can say that the second order derivative of a maximum should be strictly negative, then we're already done. Then we're done, right? Okay, so if we could, okay, but I should actually right away. Okay, actually we couldn't. Actually we couldn't. If we could, okay, if we could assert that, okay, a maximum of a function, okay, within a domain, which means that maxima is not on the boundary, okay, should satisfy, okay, partial u, okay, so let's say should satisfy that uxx is smaller than 0, strictly smaller than 0, okay, then we're done. Why we're done? This is because, you see, let's say I'm talking about here, right? Okay, this is my function, okay, this is my function, and this is the place of the maximum, okay. On the direction of x, okay, it should be the maximum. On the direction of y, it's also the maximum, right? And on the direction of x, it tells me that uxx should be smaller than 0. On the direction of y, it also tells me that uyy should be smaller than 0. Then its sum is smaller than 0. Okay, then of course, then this is because that uxx plus uyy, this thing is strictly smaller than 0, which means that this is not true. U doesn't satisfy. Okay, U doesn't solve a plus u equals to 0. Okay. Then we can already prove this. But again, don't forget this is a big proof. Okay, this is a big proof because if we could is actually wrong from the beginning. We cannot say that. But this is actually a very stimulating way for us to find the real proof. Okay, for the maximum principle. So now the real proof. Okay, the real proof. Now let's say that, okay, for any epsilon that's larger than 0, okay, I'm choosing an arbitrarily small number, epsilon, and let me call my v epsilon x, okay, to be my ux, okay, to be my ux, and then plus epsilon x squared. Here, again, the x squared means the square of the norm. Okay, the square of the norm, because now x is what? Now x is a vector. Okay, x now becomes a vector. Okay, the square of the norm. So that means that the further away my x, that my x is away from the origin, then the larger the norm is. Right, the larger the norm is, because the larger the distance. Right, the larger the distance. Here again, the x over here, that is actually the square root of x squared plus y squared plus z squared, which is the distance. Okay, the distance between x and 0. The distance between x and 0. So now, you see, what can I say about my Laplace v epsilon? What can I say about my Laplace v epsilon? What can I say about my Laplace v epsilon? So again, the Laplace is what? Is a differential operator. And that's a linear differential operator. So that should be what? That actually should be Laplace u, right? And then plus epsilon, Laplace, okay, x squared. So far so good? So far so good? What is Laplace u? What is Laplace u?
0.
0. We already know that use a harmonic function, right? So this actually equals to epsilon, okay, epsilon Laplace x squared. But what is that? What is that? Okay. So I'm talking about, okay, I'm talking about Laplace of x squared plus y squared plus z squared, right?
Oh.
Right? I'm talking about the Laplace of x squared plus, because again, this is my x. This is my x squared according to Pythagoras theorem. Okay? So what is the Laplace of x squared plus y squared plus z squared? This, let's say this is my w, okay, this is my w, x, y, z. Right? Okay, what is my wxx plus wyy plus wzz? What is my wxx? We've got 2, right? Wyy, 2. Wzz, 2. Right, so that's actually 6. Right? So I'm having this guy should be actually 6 epsilon. Oh well, actually, you know what? This I was assuming actually this is not 6. I was talking about the proof in n dimension. I'm sorry. I was talking about the proof in n dimension. So actually, instead of 3 dimensions over here, actually it should be n dimensions. So instead of 6, this actually should be what? 2n. This actually should be 2n. But it doesn't matter, right? So let's say it is actually 2. Okay, this is actually 2n epsilon. So that's good? Okay. This is actually 2n epsilon. And this is strictly larger than 0. Okay? This is strictly larger than 0. So that's good? So this is when this is strictly larger than 0. Okay? But okay. So now let's assume, okay. Okay, so sorry about that. So this is strictly larger than 0. And now what can I say? What can I say about the maximum? Okay, what can I say about the maximum of v epsilon? What can I say about the maximum of v epsilon? Can the maximum of v epsilon be attained inside the domain D? Is that possible? We have just argued that for any interior maximum, you should satisfy what? For any interior maximum, its Laplace should be strictly smaller or equals to 0. Right? See? Okay. For any, because, okay, for any interior maximum, okay, for any interior maximum, let's see, xm, right? The Laplace v epsilon xm should be what? Should be strictly smaller or equals to 0. It should be strictly smaller or equals to 0. This is again because my u is a second order differentiable function, and the same reason my v is also a second order differentiable function, which means that if my v has an interior maximum, then at this interior maximum, its Laplace should be strictly smaller. This is okay? Is this okay to everyone? Any confusion over here? Okay, this is good. But what we have just proved, the Laplace of V epsilon satisfied, right? It's strictly larger than 0 because of what? Because again, you see, the u, I don't know, because u, the Laplace of u is 0, right? So I cannot exclude the possibility that there's an interior maximum of u that such that the Laplace of u at this maximum is 0. But now, by adding this modification term, epsilon x squared, okay, now I can argue that the Laplace of my v epsilon is strictly larger than 0. It is strictly larger than 0 as long as my v epsilon is larger than 0. Right? Okay. So here, on the one hand, I know that the Laplace of v epsilon is strictly larger than 0. On the other hand, I know that if my v epsilon has an interior maximum, then the Laplace of the interior maximum should be smaller or equal to 0. What can we deduce? What can we deduce?
V doesn't have interior maximum.
V doesn't have any interior maximum, right? So that means that V epsilon doesn't have any interior maximum. Or equivalently, that means that the, let's say the xn, okay, the maximum, sorry, let me put it this way. So the R max, okay, the R max, my x belongs to D, belongs to the closure of D, okay, of Vx, okay. Actually, it belongs to the
boundary.
It belongs to the boundary of D. Okay? The maximum of V is attained at the boundary of D. Okay, now it's time for us to come back to link the V epsilon to U. Okay, now it's time for us to link the V epsilon to U. So now let's say for any x belongs to D, okay? For any x belongs to D. First of all, what can I say between ux and vx? V epsilon x, sorry. What can I say between my ux and v epsilon x according to the definition of my v epsilon x? My ux is always smaller or equals to the vx, v epsilon x, right? So that's okay. And let's say the maximum, okay, the maximum of v epsilon x is attained, okay, is attained at x0, okay, x0 of course is on the boundary. Okay. So any value, any v epsilon, any value of v epsilon x, okay, that should be smaller or equals to its maximum, right? So let's say v x0. So what's so good? So what's so good? V epsilon x0, sorry. V epsilon x0. Again, what is x0? X0 is the maximum, okay? X0 is the maximum of v epsilon. Sorry, x0 is the place that I can obtain the maximum of v epsilon. Okay? But again, what is the expression? What is the expression of v epsilon x0? According to the definition, my v epsilon x0 is actually my u x0, okay? And then plus what? And then plus epsilon x0 squared. So that's good? This is my epsilon x0 squared. So don't forget, my x0 satisfies what? My x0 satisfies that my x0 is always belongs to the boundary of D. It doesn't really matter which epsilon that I choose, right? For any epsilon that I choose, For any epsilon that I choose, I will always have that the maximum of v epsilon x is attained on the boundary. Is attained on the boundary, right? So that means that my ux epsilon, this is actually smaller or equals to the maximum on the boundary. So is it good? So is it good? Again, this is logic. No matter what epsilon that I choose, the point that v epsilon x attains maximum x0, okay, is always on the boundary. So, okay, no matter what epsilon that I choose over here, the ux0, which is on the boundary, is always smaller or equals to the maximum of value of u on the boundary. Right? And then of course plus the epsilon x0. But is x0 is this guy bounded? Is this guy bounded? Yes, this guy is bounded as long as my D is a finite set, right? As long as my D is a as long as my D is a finite set, which is that my D doesn't cover any infinity. Okay? So now we just simply need to take. Okay, take epsilon goes to 0. Now we're taking epsilon goes to 0. So that tells me that my ux, okay, my ux for any x within the domain D, okay, is always smaller or equals to the maximum of u where my x of the maximum of ux where my x is chosen on the boundary. So finally, this means that okay, the maximum of u is attained on the boundary. Okay, the maximum of u is attained on the boundary. Is there anything that's unclear in this step? I hope everything is clear. Okay. So this is the whole proof. This is the full proof. Okay, the real proof for the maximum principle. And we will be using the maximum principle. Okay, to derive the uniqueness. The uniqueness of Laplace and the Laplace equation and Poisson equation. Okay, the uniqueness of Laplace equation and Poisson equation. So now let's say, suppose that it's not unique. Okay, suppose that it's not unique. Then that means that I'm having u and v. I'm having two different solutions for the same Poisson equation or for the same Laplace equation, right? So I'm having my u and v satisfying that, okay, my Laplace u equals to f for in the domain D, okay, and my Laplace v also equals to f in the domain D, and they satisfy the same boundary condition, which is my u equals to my u or my partial u or my partial u partial n or something like that. But there's a boundary condition. Okay, they satisfy exactly the same boundary condition. Let's say h. Let's say hx. Okay, on the boundary D, and so is my v. My v or my partial v partial n. Okay, or any combination of that equals to hx on the boundary D. So much of it. Now, what can I say? About u minus v? What can I say about u minus v? Let's say my w equals to u minus v. U and v, they satisfy exactly the same equation in the domain, and they satisfy exactly the same boundary condition on the boundary. What can I say about the difference? W, which equals to u minus v.
It's a harmonic.
First of all, what can I say about the Laplace of W? What can I say about Laplace W?
It's 0.
Laplace W is equal to what? According to that, Laplace is a linear operator. Laplace u minus Laplace v. What is Laplace u? It's f. What is Laplace v? It's also f, right? So that equals to Laplace u minus Laplace v, which is f minus f, which is what? 0. Which means that the difference between u and v, w, it should satisfy the Laplace equation, right? So this is the first thing, right? And second thing, what is the boundary? What is the boundary? Okay, what is the boundary condition for w? What is the boundary condition for w? You see, my u and v, they satisfy exactly the same boundary condition, which means that they are exactly the same on the boundary. What can I say about the difference? What can I say about the difference on the boundary? U and v are exactly the same on the boundary. So what is the difference on the boundary? What is the difference on the boundary? 0, right? And so my w equals to 0 for any wx, okay, equals to 0 for any x on the boundary. Ha ha. Now, what can I say? My Laplace w is 0, okay, within the domain D, which means that my w is a harmonic function. I also know that my w is everywhere 0 on the boundary, according to the maximum principle. What can I say? According to the maximum principle, what can I say? The
The
maximum and the minimum of u can only be attained on the boundary. Now
not
my
constant
boundary
zero.
is what? Is 0 everywhere. So
It's
my
constant.
w has to be 0 everywhere. Okay, my w has to be 0 everywhere. So, okay, so according to the maximum principle, okay, maximum principle, I have that my w is smaller or equals to 0, my wx, okay, is smaller or equals to 0 for any x, okay, within D. But also according to the minimum, according to the minimum principle, my wx, okay, it can only be larger or equals to 0 for any x, okay, in D. So finally, my w is a constant 0, which means that my u and v, they are exactly the same thing. Okay, my u and v are exactly the same thing, which now proves that the uniqueness, this is how we are using the maximum principle to derive the uniqueness of Laplace and Poisson equation. Okay, so this is this is the only thing that we're going to talk about regarding the well-postedness, okay, regarding the well-postedness of the Laplace equation and Poisson equation. There are of course, okay, other aspects of that is about the uniqueness, which is the stability, and also the existence. Okay, but very unfortunately, we are unable to prove it in such a short time. Okay, so this is the only thing that I would like to focus to. And also, the maximum principle is a very useful property, okay, for any harmonic functions, telling you that the maximum, okay, the maximum, both the maximum and the minimum of both the maximum and the minimum of a harmonic function, okay, can only be obtained on the boundary, okay, but nowhere else. That's good. Okay. Good. Okay. So this is the first half of the class. Let's have a 5 minutes break.
你去了。
哦，上厕所。